When we train a classification model, we have a hidden assumption. We assume that every class the model will ever see during testing already existed during training. This is called closed set recognition. But real environments are not closed. New categories appear constantly. And when a new category is encountered, the model must say, I don't know this class. Instead, standard neural networks confidently misclassify unknown inputs as known classes. This failure is known as the open set recognition problem. So usually a classification model has two parts, an encoder and a classifier. So the encoder creates an embedding space and the classifier draws the boundaries. And in this problem, we want to make sure that the embedding space is spacious enough so that we have enough open space to put these new categories. And to solve this problem, the authors are proposing using a new representational space on a unit hypersphere. Because most of the time when we train these models, we use the Euclidean space as the representational space, and as a result the representations can grow indefinitely. And so to avoid this, unit hypersphere is the best solution. Every embedding now has a fixed magnitude. Only direction matters. On this hypersphere, each class is modeled using a von Mises-Fisher distribution, which can be thought of as a Gaussian defined on a sphere. Each class has a mean direction and a concentration parameter. This creates a bounded and interpretable geometry. So the method introduces three main ideas. First, spherical representations. By normalizing embeddings, the model balances two properties, alignment and uniformity. Together, these create separable and structured features. So the separability is really important. Second, orthogonal label embeddings. Each class prototype is forced to be orthogonal to each other. Each class lives in its own subspace, and as a result, we can be confident that these features are not depending on each other. Third, mix-up and label smoothing are applied during representation learning, as you can see here. Mix-up creates ambiguous samples that simulate unseen categories. The model learns how uncertainty should look geometrically, pushing ambiguous samples away from class centers and reducing the familiarity trap. And training happens in two stages. Stage 1 learns a structured spherical representation using these constraints. Stage 2 freezes the encoder and trains a simple classifier on top of it. Because the representation space is already well organized, even simple scoring rules can detect unknown samples effectively. And experiments show that shaping representations directly leads to strong improvements across open set benchmarks, especially when unknown classes are semantically similar to known ones. And this suggests an important shift. We must shape the representation space itself, and designing the geometry of the feature space itself allows us to avoid this open set recognition problem.